Hello, dear friends. Myself, Dr. U.A Deokate, Associate Professor, Government College of Pharmacy, Aurangabad. Welcome you to my second lecture on optical method of analysis. Today we will learn the learning outcomes of today's lecture. The learner will be able to define electromagnetic radiations and electromagnetic spectrum and spectroscopy. Explain different characteristics of electromagnetic radiations. Relate energy content of radiation with interaction with matter. List different spectroscopic technique. These are the learning outcomes of today's lecture. First of all, we will see what you mean by electromagnetic radiation. Electromagnetic radiation is energy that is propagated through the free space or through the material medium in the form of electromagnetic wave. The radiations which can travel from one point to another point is called as electromagnetic radiation. It has both vector, electrical field and magnetic field, therefore the term electromagnetic radiations. The magnetic and electrical field comes at 90 degree to each other and the combined wave moves perpendicular to both electrical and magnetic oscillating fields. What are the various characteristics of electromagnetic radiation? Now, pause this video, record your answer onto the notebook and restart the video. I think all of you have written the answers. Now we'll play the video and see the answer. Electromagnetic radiations has properties of waves such as reflection, refraction, diffraction, interference, and frequency with which it varies over the time and wavelength. Electromagnetic radiations, however, has particle-like properties in addition to those associated with the wave motions. It is quantized in that for a given frequency, its energy occurs as an integral time h, in which h is a fundamental constant of nature known as Planck constant. A quantum of electromagnetic energy is called as a photon. Visible light and other form of electromagnetic radiation may be thought to be of a stream of photons, with photon energy directly proportional to the frequency. So as the frequency increases, so the photon energy content also increases. We will see certain characteristics of electromagnetic radiations. Electromagnetic radiations travels in wave form at constant speed. The wave characteristic of electromagnetic radiations are found in relationship of velocity to wavelength and frequency. Frequency, that is cycles per seconds, which is measured in hertz, expressed in the formula as c equals to lambda v, where c is a velocity of light, lambda is a wavelength of radiation, and v is a frequency. Because the velocity is constant and any increase in frequency results in subsequent decrease in wavelength. Therefore, wavelength and frequencies are inversely proportional. So as the wavelength increases, frequency decreases. All forms of electromagnetic radiations are grouped according to their wavelength into an electromagnetic spectrum. Now you can see this, the radiations which are broken into the electromagnetic spectrum, which starts from gamma rays. So it is in continuum. First we will have gamma rays followed by X-rays, then ultraviolet rays, then visible rays, infrared rays, then followed by microwave rays, radio frequency rays, then TV rays and radar rays. Out of this, for the analytical purpose, we are using X-rays radiation to radio frequency radiations. You can see on this picture that on the other side, as this wavelength increases, this is increase in wavelength. As you go towards the radio frequency region, the wavelength increases and the energy content decreases. Okay. Similarly, if you see, as the wavelength increases, frequency decreases. So on this side, at the higher energy level, frequency is also high and the energy content of radiation is also high. This is a very important statement I am doing because this will relate the interaction of electromagnetic radiations with matter. So how much the radiation possesses the electromagnetic energies. We are considering light as a part of electromagnetic radiation. Only this very small part of visible light will be considered as a light. So this electromagnetic radiation is a spectrum that you are most familiar is a visible light. But this is just a small portion of all the possible types. So it is divided into seven colors, that is violet, indigo, blue, green, yellow, orange and red, that we call as a wave. So these radiations are not of the single wavelength. It is available in form of a band. So if you says violet, the wavelength of this violet light will be from 400 to 420. In that way, every color is in the form of a band. Band of radiation means similar kind of radiations. Similar kind means if you says yellow light, it will be not dark, it will be dark yellow, it will be faint yellow, it will be greenish yellow, it will be reddish yellow. In that way, we can have certain tinge and every tinge will be recorded as a single wavelength. So they are called as a monochromatic. Chrome means color. Color is related to its wavelength. So this is all in the visible region. But rest of the radiations, they doesn't has the color. So they are also useful in the analytical purpose. One more important thing that we are discussing is the complement color. So we are not interested what color is observed, but we are interested what color is absorbed, because these radiations will fall on the matter and it absorbs those radiations, and the amount of radiation absorbed is important for analytical purpose. So the color observed with your eye is the color reflected. What we are interested is in the color absorbed, which is known as a complement of the color observed. So we have given a list of various colors and their complement color. Okay, if you see violet color to your eyes, the absorbed color is green and yellow. So this is how the various complement colors are listed in this table. We will have certain definitions of terms which are used in this lecture. First, we will discuss about the wavelength, which is denoted by lambda. It is defined as the distance between the adjacent peaks or troughs and may be in designated by angstrom, meters, centimeters or nanometer. That is 10 raised to 9 meters, 10 raised to minus 9 meters. So this is the wavelength which we are commonly utilizing with the unit. The second characteristic definition is a frequency, which is denoted by small v. It is a number of wave cycles that travel past a fixed point per unit time and usually given in cycle per seconds or hertz. So this is how many waves are passing from a fixed point is called at its frequency. As all of you know, we can say the frequency of bus is very less. Means from that point, very few buses are passing. Similarly, here also it is time-based phenomena. How many waves passes from a fixed point are to be considered as a frequency. The another parameter or characteristic is the wave number. In many spectroscopy, we are using this wave number. It is denoted by small v bar. This minus size is on the top of this v. Is a number of waves per centimeter. It is usually given in centimeter inverse. So in 1 centimeter, how many waves are sitting, that we are calculating, that is called as a wave number. The another characteristic is velocity, that is given as a c. It is the speed of light is perpendicular to the medium, usually given in centimeter per second or meters per second. So these are certain definitions, you need to by heart them. then we will have certain correlations between the characteristic. Frequency and energy changes proportionally. Means as the frequency increases, the energy content of radiations also increases. The wavelength has an inverse relationship to these quantities. Means as the wavelength increases, the energy content of radiation decreases. The frequency and wavelength are related by velocity of light c by the equation lambda equals to c by v, or we can write as v equals to c by lambda, where v is a frequency, lambda is a wavelength, and c is a velocity of light. So c generally we can take it as a t 3.10 into 3 into 10 raised to 10 centimeter per second. So we are talking about the energy, that is delta E, which is equals to hv, Planck constant. The E is the energy, V is a frequency, and H is a Planck constant. Its fixed value is 6.6 into 10 raised to minus 27 earth per second. So why we are considering all this relationship? In many cases, we need to convert one unit to the another unit by using these formulas. The frequency and wave number can be correlated, that wave number equals to V by lambda, and wave number can also be correlated as V bar equals to 1 by lambda. So just if we know one quantity, we can calculate the another quantity by using these formulas. Now we will discuss about what is spectroscopy. Spectroscopy is a study of interaction between electromagnetic radiations and matter. This term is very important. Spectroscopy is a study of interaction between electromagnetic radiations and matter. There are different types of spectroscopy depending upon energy content of electromagnetic radiations and interaction with the matter. Electromagnetic radiation can interact with molecules or atoms or ions. Depending upon that, the spectroscopy can be classified as molecular spectroscopy. If the interaction of electromagnetic radiation is with molecule, it is called as a molecular spectroscopy, and if interaction is with atom, it is called as an atomic spectroscopy. Many times in spectroscopy, we are using various terms like spectroscopy, spectrometry, spectrophotometry. So many times we get confused. What is the difference between this term? Spectroscopy, in practice, the term spectroscopy and spectrophotometry are used interchangeably except for mass spectrometry. But the two words doesn't mean exactly the same things. Spectroscopy comes from Latin word specere, meaning to look at, and the Greek word scopia, means to see. The end of spectrophotometry comes from Greek word metra, meaning to measure. Spectroscopy studies the electromagnetic radiations produced by system, or the interaction between the system and light, usually in a non-destructive manner. Spectroscopy is a measurement of electromagnetic radiation to obtain information about the system. In other words, spectrometry can be considered a method of studying the spectra. Example of spectrometry include mass spectrometry, Rutherford scattering spectrometry, ion mobility spectrometry, and neutron triple axis spectrometry. The spectra produced by spectrometry are, aren't necessarily are generally plotted as the intensity versus frequency or wavelength. For example, a mass spectrometer, a spectrum is plotted intensity versus particles masses. The another term which we are commonly using is spectrophotometry, is a method to measure how much chemical substance are absorbed by the light by measuring the intensity of light beam which is transmitted through the sample. The basic principle is that each compound absorbs or transmits the light over a certain range of wavelength. This measurement can also be used to measure amount of known chemical substances. So spectrophotometry, we are using this term for quantitative estimations, whereas the spectroscopy and spectrometry we are using for qualitative determinations where the structural elucidation process is to be considered. So these are the three terms which are interchangeably used in the spectroscopy. Generally, what is the use of spectroscopy? Spectroscopy can be used to identify the nature of compound in the sample. It is used to monitor the progress of chemical process and to assess the purity of product. It can also be used to measure the effect of electromagnetic radiations on sample. In some cases, this can be used to determine identity or duration of exposure to the radiation source. Now, we'll consider the classification of spectroscopic technique. There are multiple ways to classify type of spectroscopy. The technique may be grouped according to type of material being studied, whether these radiations are bombarded on atom, crystals, molecules, atomic nuclei, etc. So depending upon that, we can classify the spectroscopic technique. The another method is the interaction between the material and the energy. So what happens when the radiations are bombarded onto a matter, whether emission take place or absorption of electromagnetic radiation take place or electric scattering take place. So this is another method to classify the spectroscopic technique. And third one is your specific application, that is Fourier transformation spectroscopy or circular dichroism spectroscopy. So these are the specially designed spectroscopic techniques, alteration into the conventional spectroscopic technique. So we are talking about the electromagnetic radiations and various types of spectroscopy. We will have a chart to discuss the usual units in meter, frequency and wave numbers of certain radiations which are used in different spectroscopic technique. First we will see the X-ray spectroscopy, X-ray diffraction and X-ray absorption spectroscopy, where X-ray radiations are to be used. So their usual unit, we are counting it in terms of the angstrom, 10 raised to minus 2 to 10 raised to plus 2 angstrom. So we can consider this in unit of meter to consider the continuation of this electromagnetic radiation. It is 10 raised to minus 12 to 10 raised to minus 8 meters. The frequency is there, that is 10 raised to 20 to 10 raised to 16 hertz, and wave number is given in centimeter inverse. As these radiations are very closer, their wavelength is very small, we are not able to measure how many waves are sitting in 1 centimeter. So wave number is not possible for the X-rays. Similarly, it is followed by far UV, that is also sometimes called as a vacuum UV, that is between 10 to 200 nanometer. So you have to by heart these values because it will be always used. So usual unit is 10 to 200 nanometers. In meter you can see the X-rays are ending at 10 raised to minus 8 and UV vacuum is starting at 10 raised to minus 8 to 2 into 10 raised to minus 7. The frequency is there 10 raised to 16 to 10 raised to 15 and there is no wave number. Vacuum UV is followed by near UV, which is lying from 200 to 400 nanometer. Its units in meter and frequencies are listed. Then it is followed by visible radiations, that is 400 to 750 nanometer. The units in the meter, again they are in the continuation to the previous one, and frequency. Here one thing you can observe, the visible rays, the wave number is shown, that is 25,000 to 30,000. Means we can count how many waves are there in 1 centimeter square area. Therefore wave number appears from visible region. Then comes your near IR region. IR region is divided in three parts: near IR, mid IR, and far IR. The general unit of your IR measurement is in micrometer. So here visible range ends with the 750 nanometer, and we can convert it if into the micrometer, it will be 0.75 micrometer. So your near IR start from say a 0.75 micrometer to 2.5 micrometer. Its unit in meter are again continuum with the previous one. Frequencies are written. Now in case of IR, we are using this wave number as a general unit for measurement. If you observe the IR spectrum, wave number are always written there. So near IR, they are between 13,000 to 4,000 centimeter inverse. Near IR is followed by mid IR, that is 2.5 to 50 micrometer. So it's again unit in meters are in continuum to understand the continuity of the radiations. Frequencies are written and the wave numbers are from 4,000 to 200 centimeter inverse. So mostly our IR spectroscopy lies between this mid IR region. Then comes the far IR, that is from 50 to 1000 micrometer, and its wave number is 200 to 10 centimeter inverse. After far IR, the microwaves are coming. See here, as you are going towards the higher wavelength side, the energy content of the radiations are decreasing, and as there is change in energy content, their interaction with the matter also varies. So that is very important phenomena of all the spectroscopic technique. So in microwave, that is zero point 0.1 to 100 centimeter, usual unit is in centimeter, and it has a wave number of 10 to 10 raised to minus 2. Here up to this we can measure the wave number. After then it comes the radio waves, which is in the 1 to 1000 meters, and we are unable to measure the wave number in this case. So these are the various regions of electromagnetic spectrum, and in each region one spectroscopy lies that we have to study. X-ray, X-ray diffraction and X-ray absorption. In far UV there is no spectroscopy. In near UV we are having the UV spectroscopy. In visible, that is UV visible spectroscopy is there. In near IR, no spectroscopy. Mid IR, infrared spectroscopy we have to study. Then far IR, no spectroscopic technique is available. In microwave, electron spin resonance spectroscopy can be studied, and in radio waves there are the nuclear magnetic resonance spectroscopy, that is NMR. Two types of NMR we are going to learn, that is your C13 NMR and PMR. So this is all about the types of radiation. You prepare one chart and keep it with you. So this will be helping you to understand the frequencies and the wavelengths of each radiation. Thank you and happy learning, dear friend. See you in the next video.